I'll begin with finite sums. This corresponding section in the notes is 30 pages long. I will try to get under 30 minutes, and I will try not to do this by talking fast, but instead I will try to avoid all the fairly straightforward and commonplace results that are in the notes. I think you should be using the notes as a backup here, because a lot of properties of sums are really very much obvious if you look at them just as big sums of numbers. They're not as obvious if you define everything by induction and try to prove things formally, but that's not the point of this course. In the notes, I actually state everything. Here, we're just going to see how to use these results. So what's the most general notion of a finite sum? You probably mostly have seen this kind of finite sums. Sum from I equals u to v ai. I will generalize them a little bit. I will define sum over all elements of a given set. And that set will be a finite set. So I won't generalize it that much. I don't want to go into analysis. So let's give the definition quickly. This should not surprise you. It's just a formal way to define something you already know. If S is a finite set, and if AS is a number for each S and S, so number means rational number, real number, complex number, non-negative integer, integer, whatever you want. Then this sum denotes the sum of all of these numbers AS. How is it formally defined? It's defined by recursion on the size of S. And it's just a good thing to recall how it's defined, even so you really know how to compute it. If the size of S is 0, so we're summing over the empty set, then it's defined to be 0. This is called an empty sum. Empty sums are 0 by definition. And now what happens if you, so if the size of S is non-zero, the recursion step looks like this. Let n be a non-negative integer. Assume that we have defined the sum already for every finite set S with size n, and for all numbers AS. Now let's define it for sets of size n plus 1. So if S is such a set, and if AS are numbers, then how do we define it? We pick any element T in S. We can do it because the size of the set is at least 1, and therefore the set is non-empty. And we set this here. So what we're doing is we're picking an element, we're removing it from the set, we're adding all the other elements, and we're adding that sum to that one term that we have removed. So informally, so what is this really saying? That we compute the sum of elements of S by starting with 0, that's this base case, and adding the numbers AS one by one. And you might notice something. It's absolutely not obvious that this is well defined, because we have a choice of T here. We can pick any T. And here we don't specify the order in which we add these numbers. Well, it turns out that this is not a problem. The order is immaterial. It doesn't matter which T we pick here. Every time we get the same result. But this is a non-trivial fact that needs to be proved. So in the notes, I give a reference to a place where I really fully write up the proofs that this is well defined. You shouldn't worry about it unless you feel like worrying about it. It's a very basic fact that's more or less implicit in anything you're doing in mathematics. Just as a hint to proving this, this is proved by induction, of course. How else? And it's not obvious. The same would not be true if you would, for example, for multiplying matrices, you would start with the identity and you would multiply the matrices one by one. Well, in that case, the order would matter. Similarly, I think when you're taking on clothes, it matters what you put on first. So in real life, things don't behave this way, but numbers are nice. So we have defined a sum, and there is a specific notation for specific sums, namely, if u and v are integers, then this summation sign is so a sum from s equals u to vas is defined to be the sum over all elements of the set u plus 1, u plus 2, and so on v, as. So this familiar summation sign is just a particular case of this summation sign when the set is an interval of integers. A few more words. So the sign, this here, is called a summation sign, or just sigma sign. It's shorter. And the s in this thing here is called the summation index. And of course, nothing requires you to call it s. You can rename the summation index as you wish, just as an argument in a function. Just make sure that if you rename it here, you also rename it here. For example, this here, you can rename the s as a t. Just don't rename it as something that already has some different meaning. And in this sum, the u and the v are called the lower and upper limit, or sometimes we call them bound of the sum. This has nothing to do with the limits in analysis, like the limits of sequences, nor with the bounds in analysis. So this is just a way to say the sum begins at u and ends at v. Here is a little convention. If u is bigger than v, then the set from u to v, the only reasonable way to define this is just to say it's an empty set, because there is nothing between u and v. U is already bigger than v. So in this case, the sum is going to be a sum over an empty set. As we know, that's an empty sum, so it's 0. A few more words on notation, because there is some pitfalls here. So commonly, if you see something like this, it means that everything here is inside the summation, so to speak. However, if you see something like this, that's not clear. It could mean this plus b, but it could also mean the sum of the sum. So it might mean either this or this. And those are two different things. So I would be careful. And different authors actually mean either this or this. There is no standard. So for me, it will always mean the latter. So it will always mean this here. But this is only one of the possible conventions. Be watchful when you're reading.